So let's attempt to apply Ohm's law to this example problem that shows a combination of resistors that are in parallel and series connections. So we refer to this as a reducible circuit because we can replace the whole network of resistors with one equivalent resistance. A good first step is to identify any junctions. So maybe I'll label these junctions X and Y. It might also be helpful to choose a frame of reference where electric potential equals 0. So we draw in the symbol for ground, and then we note that V equals 0. And then maybe even show the current that flows through the battery. Okay, so we've got some current we label as I, and we see that current flows out of junction Y and into junction X, and along the way flows both through the battery and through the 15 ohm resistor. Now that current's going to break up into two paths. So once the current reaches junction X, then it splits off. Some of that current, maybe we'll call it I1, flows through the 6 ohm resistor. And another value of current, we can call it I2, flows through both the 20 ohm and the 10 ohm resistor. Now I1 and I2 are going to recombine at junction Y, and they should add up to give us our original current, capital I. Okay, so now the next steps are to start to figure out which resistors we can combine together and ultimately form one equivalent value of resistance. And you should see that the 20 ohm and the 10 ohm are without a doubt in series with one another. See, that current that we labeled as I2 is the same current through both the 20 ohm and the 10 ohm, and when two resistors have the exact same current flowing through them, they're probably in series. I say probably in series because you could have paths that coincidentally have the same amount of current. I guess the idea is if there's only one singular path formed by two resistors, then they're in series. So in any case, now it seems like we have a 15 ohm that's in series with a combination of a 6 ohm and a 30 ohm. And by the way, that current that we had labeled as capital I, we still see flowing through the 12 volt battery and the 15 ohm resistor. It reaches our junction at point X, and it splits off into the current we labeled as I1. And that other current that we had labeled as I2 now appears to be flowing through just some single amount of resistance. Okay, so we continue reducing it. Now we recognize that the 6 ohm and the 30 ohm are in parallel. Now what's the rule? 1 over the equivalent resistance is 1 over R1 plus 1 over R2. So 1 over the value of R we're looking for is equal to 1/30th plus 1/6, but we can replace 1/6 with 5/30ths, so we get a total of 6/30ths, which is the same thing as 1/5. So if 1 over R is equal to 1/5, then R is equal to 5, and that's shown here. Of course, the other way we could have done it is said, since it's just two resistors, we could use that formula that says we take the product over the sum. So 30 multiplied by 6 over 30 plus 6 gives us 180 over 36, which you would still agree is 5 ohms. Okay, so now the current that we had labeled as capital I that flows through the battery and flows through the 15 ohm resistor then also flows through this equivalent resistance of 5 ohms, and now there's really just one amount of current to consider. So the 15 and the 5 are now in series, and don't need to show the math of where this 20 comes from. Alright, so now we've really reduced this circuit as simple as we can make it, and at this point we want to create some sort of graphic organizer to help fill in the values. So there was a 15 ohm resistor, our original 6 ohm resistor. The 20 ohm and the 10 ohm are in series with one another, and then we have an overall equivalent resistance of 20 ohms. So it's that overall equivalent resistance of 20 ohms that has the voltage of 12 volts. So the current can be found by Ohm's law. Let's write it in its triangle form. So if we're trying to solve for current, we divide voltage by resistance. So 12 divided by 20 is the same thing as 1.2 divided by 2. Or in other words, we have 0.6 amps. So this is 0.6 amps. So we trace it back. It's still 0.6 amps here. Now, we can apply Ohm's law individually to any given resistor. In other words, the voltage drop across this 15 ohm resistor is the product of the current through it times its resistance. So we get 0.6 multiplied by 15. What is that? 9, right? 9 volts. So we're saying the electric potential here is 0. So here it's 12. And then there's a voltage drop of 9 volts. So the voltage is down to 3 here, which means the voltage across the 5 ohm resistor gets us from 3 volts back down to 0 volts. Now is this right? When we use Ohm's law and say V equals IR, when we multiply the 0.6 amps flowing through 5 ohms of resistance, yeah, indeed, we get 3 volts. So it seems to match up nicely. We can fill in those values then. The 15 ohm resistor has 9 volts across it, and it also has that 0.6 amps flowing through it. Okay, so we continue working our way back up our individual diagrams here. 0.6 amps is the current that flows into junction X, and then it splits up into I1 and I2. Now, we know the electric potential here is 12, 0, and then we found the electric potential at point X is 3 volts. The electric potential here is 0, down here is 0, 3 volts. So if I were to hook a voltmeter across the 6 ohm resistor, the potential drops from 3 volts down to 0. In other words, there's 3 volts across the 6 ohm resistor. If I hook a voltmeter up across this 30 ohms of resistance, again, gets me from 3 volts to 0 volts, so a potential difference of 3 volts. Now there is no individual 30 ohm resistor. That was really the combination of this 10 and the 20. In any case, we could at least work on this row. I is equal to V over R, so when we divide 3 volts by 6 ohms, we get 0.5 amps. Okay, so of the 0.6 amps that flows into junction X, 0.5 of those amps flow through this part of the circuit, which means by Kirchhoff's junction rule, we expect this value of I2 to be 0.1 amps. Now let's see if that works out. If 0.1 amps were to flow through 30 ohms of resistance, well, V equals IR, so 0.1 times 30 would indeed give us the 3 volts that we expect. Another thing to notice is that the current flowing through 30 ohm resistance is 0.1 amps. The current through 6 ohms is 0.5 amps. Well, 6 ohms is 1/5 as much resistance as 30 ohms. So it's reasonable that 5 times as much current is flowing where there's 1/5 as much resistance. And kind of neat to see how the ratios work out. Okay, so we trace our way back up the diagram. This represents 0.6 amps. Of that 0.6 amps, 0.5 flow here, and 0.1 amps flows here. So if I want to find the voltage across the 20 ohm resistor, Well, I can fill in. Let's see, we know this is 0.1 and this is 0.1, and V is just equal to I times R. So 2 volts across the 20 ohm resistor, right? I multiplied 2 times 0.1. I multiplied current times voltage according to Ohm's law. I'm sorry, I multiplied current times resistance according to Ohm's law in order to find the voltage drop. So same thing, if I multiply 0.1 times 10, I get 1 volt. And by the way, 2 volts plus 1 volt gives me 3 volts, right? The voltage drop, here the electric potential here is 3 volts, and then there's a voltage drop equal to I times R, so 0.1 amps times 20 ohms gives me 2 volts. Okay, so the electric potential here is 2 volts less than 3, so it's down to 1 volt. And then if I multiply the current times this resistance, 0.1 amps times 10 ohms, I get 1 volt. Perfect, brings me back down to 0. Everything seems to work out. And so once you get to the point where this chart's filled out, then to find the amount of power in any given resistor, or the power consumption of any given resistor, we can either use the equation says multiply current times voltage, or we can multiply the current squared times the resistance, or the voltage across that given resistor squared divided by resistance. So probably the easiest of all is to just say it's current times voltage. So the power consumption of the 15 ohm resistor is 5.4 watts. The power consumption of the 6 ohm resistor is 1.5 watts. The power consumption of the 20 ohm resistor is 0.2 watts. And the power consumption of the 10 ohm resistor is 0.1 watts. Now, how do we find the overall power consumption of the whole circuit? Well, we could simply multiply the total voltage from the battery times the current through the battery. So 0.6 times 12 would give us 7.2 watts. But the other thing we notice is, what if we just added up all the individual power consumption? So let's see, 5.4 plus 1.5 would give us 6.9. 6.9 plus 0.2 would give us 7.1, and 7.1 plus 0.1 would give us 7.2. How about that? So there's ways to double check your work when doing these reducible circuit problems. No matter how you slice it, the values have to agree when you choose 2 different methods to come to the same answer. And there you have it. A straightforward example of the application of Ohm's law to what we call a reducible circuit. Now, not all circuits are reducible, and we'll find that in those cases there's still an approach that we can use based off of Kirchhoff's junction and loop rule. So stay tuned for that upcoming lesson on non-reducible circuits. And as always, thanks for watching.